Airbags are a critical safety feature in modern vehicles, designed to protect drivers and passengers during a collision. The deployment of an airbag involves a rapid chemical reaction that generates a large volume of gas, inflating the airbag in milliseconds. This simulation will explore the stoichiometry and kinetics of three common chemicals used in airbag systems, namely sodium azide, ammonium nitrate, and nitroglycerin. We will simulate their performance to determine the most effective compound for airbag deployment. Mechanism of airbag deployment. When a vehicle experiences a sudden deceleration, typically during a crash, a sensor detects a change in speed and triggers an electric current. This current activates a heat source within the airbag canister, initiating a chemical reaction that rapidly produces a large volume of gas. The gas inflates the airbag, providing a cushion that absorbs the impact and protects the occupants from serious injury. Let's take a look at the three chemicals and their reactions in airbags. 1. Sodium azide is the most commonly used chemical in airbag systems. The compound decomposes to give sodium and nitrogen gas. This reaction produces nitrogen gas, which is non-toxic and inert, making it safe for occupants. 2. Ammonium nitrate decomposes to produce nitrogen gas and water vapor. This reaction produces nitrogen gas, however. The presence of water vapor can affect the inflation dynamics. 3. Nitroglycerin is a highly explosive compound that decomposes to produce a mixture of gases. The reaction produces a variety of gases, including carbon dioxide and nitrogen, which can inflate the airbag. Simulation parameters. To simulate the performance of these chemicals, we will consider the following parameters. Moles of chemical, increase from 1 to 2 moles. Volume of gas produced, measured over time. Reaction time, the time taken for chemical to fully react and inflate the airbag. Simulation results. 1. Sodium azide. 1 mole produces 1.5 moles of nitrogen gas. 2 moles produces 3 moles of nitrogen gas. Reaction time, approximately 30 to 40 milliseconds. Volume versus time shows a rapid increase in volume within the first 20 milliseconds, reaching a plateau shortly after. 2. Ammonium nitrate. 1 mole produces 1 mole of nitrous oxide and 2 moles of water. 2 moles produces 2 moles of nitrous oxide and 4 moles of water. Reaction time, approximately 40 to 50 milliseconds. Volume versus time shows a slightly slower increase in volume compared to sodium azide, with more gradual plateau. 3. Nitroglycerin. 1 mole produces a mixture of gases totaling approximately 7.25 moles. 2 moles produces a mixture of gases totaling approximately 14.5 moles. Reaction time, approximately 20 to 30 milliseconds. Volume versus time shows the fastest increase in volume, reaching a plateau almost immediately. Analysis and recommendation. Based on the simulation results, nitroglycerin demonstrates the fastest reaction time and the highest volume of gas produced, making it the most effective chemical for rapid airbag inflation. However, nitroglycerin is highly unstable and dangerous to handle, which poses significant safety risks during manufacturing and storage. Sodium azide, while slightly slower in reaction time compared to nitroglycerin, is stable and produces a sufficient volume of non-toxic nitrogen gas. Its reaction time of 30 to 40 milliseconds is well within the acceptable range for airbag deployment, ensuring that the airbag inflates in time to protect the occupants. Ammonium nitrate, although it produces a good volume of gas, has a slower reaction time, and the presence of water vapor can affect the inflation dynamics, making it less suitable for airbag systems. Conclusion. Considering the balance between reaction time, gas volume, and safety, sodium azide is the recommended chemical for airbag systems. Its stability, non-toxic gas production, and adequate reaction time make it the most reliable option for protecting drivers and passengers during a collision. Further research and development can focus on optimizing the reaction conditions and improving the deployment mechanisms to enhance the overall safety and effectiveness of airbag systems.